All right, welcome back, everyone. This is Mastering GLSL in TouchDesigner. We are on our 8th lesson. My name is Lake Heckerman, and I am teaching this course. I'm a new media artist. I explore how technology can alter human perception and the way that we can connect with other people. I do this primarily through interactive installations that can incorporate a lot of cutting-edge computer graphics and machine learning to really understand these new technologies and how they can apply and distort our lives. Here's some work that I've created using techniques that I'm covering in this course. I've talked about this a lot, so I won't go more into it for this course, but wanted to highlight. And then without further ado, we are on, like I said, lesson 8, cellular noise and Voronoi diagrams. So, similar to the last lesson, I'm going to be going through some slides, and then we'll jump into the TouchDesigner portion. For those of you just joining, definitely make sure to review the previous course lessons and do the exercises and grab the example files on my Patreon to make sure that you're caught up, because we are building quite quickly at this point on stuff that we have covered in the past. So with that said, let's get in. So what is cellular noise? Last time we talked about procedural noise as being functions that sample random values and then interpolate between them in interesting ways to come up with organic looking patterns. So cellular noise does a little bit different. Takes a little bit of a different approach here. And instead of sampling random values, it actually uses a distance calculation to calculate the distance from every pixel in our texture to some set of points that we will define. And the distance is what determines that pixel's color. So this is how we can create a texture that's very similar to a Voronoi diagram, which is essentially an algorithm to partition space into regions that are based on the distance of each point in that region to a specific set of interesting points. So I'm sure everyone has seen a Voronoi diagram. I have a picture of that here on the left, and then cellular noise here on the right. So it's pretty clear that you can see the Voronoi diagram, the kind of boundaries come from these boundaries in the cellular noise calculation. And that is something that we will be exploiting in this lesson. Now, before we get into all of that, there is a new topic that we need to talk about, and that is for loops in GLSL. Now, for loops are very common in programming. I bet that a lot of you have seen something similar to a for loop already. In GLSL, they are pretty similar to C++ for loops, or like a C-like language. We're going to define an iterator, which is going to be an integer. This is normally I. And our for loop is basically going to execute whatever code we put inside the for loop. Every time it executes, our iterator will go up in value, generally by 1, but we can define that specifically. And then it'll execute the code again with the new value of our iterator. It will continue to do this as long as the execution conditions for the for loop are true, and then it will stop once that execution condition is no longer satisfied, which generally means once our iterator exits some certain range that we're interested in. And then, lastly, we can define what that increment for the iterator each time through the loop is. And so here I have a couple examples. Now we're going to get into using all of this very shortly, but yes, just kind of for clarity and to ensure that all of the information is here. On the very far left, we have the most simple for loop. This is creating an iterator called I, setting it equal to some number, start index, that's commonly 0. Then you'll see the second term in this loop, I less than end IDX. that's going to be the evaluation condition. So as long as I is less than whatever that end IDX is, for example, like 10, the for loop will execute. And then I++, the very last term here, that tells us that every iteration through the loop, we're going to be increasing our iterator by an increment of 1. And then we do something each iteration. So here's an example using an integer called I, setting that equal to 0. Then running our for loop as long as the the iterator, is less than 10. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then in this case, well, we're actually adding 2 to the iterator each time. So instead of 1, 2, 3, 4, etc., it's really going to be 0, 2, 4, 6, 8. And then last, I have, we defined an integer variable called num iteration, set that equal to 10. I'm using that here in my evaluation expression. And in this case, we are initializing our iterator I equal to 0, but then we are multiplying it by 2 each time through the loop. So in this case, we're going to start with 0, and then it will be, well, 0 times 2 is 0. So that's actually a mistake. It should be, let's say if we're going to multiply by 2, starting with I equals 1, and then the next time through the loop, I will equal 2, and then the next time through the loop, I will equal 4, and then the next time through the loop, I will equal 8. And then, well, as long as our number of iterations is set to 10, that'll be it. Because 8 times 2 is 16, which is greater than 10, which means this expression is no longer true, which means the for loop will execute and not evaluate. So those are for loops. They are mildly dangerous, I would say, in GLSL because they can increase the number of computations that you do each shader pass quite substantially. Depends how many iterations we're going for and what we're doing on each of the iterations. But it is a very common programming structure, and it's something that we're going to be using to implement these algorithms. So I want to talk about it now, and we'll start to implement them in practice very shortly. So now back to the cellular noise itself. Well, first we're going to need a set of points. Points can either be implicitly calculated by using a function, or we can set up a bunch of points in like a lookup table, and then use a lookup table to sample those points. Then we can use this distance function to calculate the distance between a pixel and our point. So P0 here might be our pixel, and then P1 could be the point from our lookup table. We're going to use one of those for loops to iterate through all of the points that we're interested in and determine which is going to be closest, or really like what the minimum distance is. And then we'll color the pixel based on that information. And that is how we create a cellular noise in GLSL. So this is an example of that shader. Again, we're going to be writing this ourselves, so don't worry too much about it. But again, wanted to kind of talk through things. So for this implementation, we're going to be using a chop array as a lookup table for points. There's this new function texture size that we can use. It's a built-in GL function that tells us how big a texture is that we're looking at. And so because our chop array is going to be a one-dimensional texture, we're going to have the texture size value will tell us how many points we're iterating over. So we can actually use that to set the conditions for our for loop. We'll go through our for loop, we'll check each point, calculate the distance, and we'll keep track of the minimum distance. And then, we will just use that minimum distance to illustrate, which is to illustrate based on the color of the point, or color of the pixel, which point it's closest to. And then lastly, we'll draw the points. So we'll do that right now, actually. I think is a good place to transition to the TouchDesigner portion. We'll take a look at what we're going to be building. And again, from here, the rest of this video and the project file is going to be behind Patreon. So go over and subscribe to my Patreon to be able to access the rest of this lecture. Again, I'm doing that so that I can keep the quality up, make sure that the delivery is exactly the way that I want it. And frankly, also because there is quite a bit of work that I've put into creating this course. And so I appreciate all of the support from you on that. With that said, let us begin.